Video lesson enthalpy change of reaction. In this video lesson we're going to learn about the idea of enthalpy change, and we're also going to understand how you can calculate enthalpy changes using experimental results that you've obtained in the laboratory, and we'll also look at some basic ideas: exothermic reactions, endothermic reactions, standard conditions, and the idea of enthalpy change of reaction. Okay, a few basic ideas. First important idea is the idea of enthalpy. So, enthalpy is heat energy, and the enthalpy change in a reaction is the change in heat energy, the heat energy that's either given out or taken in from the surroundings. So often you'll see reactions represented as enthalpy level diagrams. So on the left here we've got the enthalpy level diagram for an exothermic reaction. So you can see in this reaction the reactants start off with more heat energy than the products. So energy is being given out to the surroundings during the reaction. So in an exothermic reaction you'd feel heat energy being given out. So an example of this would be a combustion reaction, Bunsen burner burning methane gas. On the right we've got an endothermic reaction, and in an endothermic reaction heat energy is taken in from the surroundings. So the reactants start with more energy, less energy than the products, and during the reaction heat energy is taken in from the surroundings. So in this reaction you'd feel the beaker getting cold as heat was taken in to the reactants. Delta H is the heat energy transferred. So the delta, the Greek letter delta, means the change, and the H represents enthalpy. So one other important idea that you're going to need later on is that in an exothermic reaction, delta H is negative. For instance, you might have an exothermic reaction with an enthalpy change of minus 75 kilojoules per mole, whereas for an endothermic reaction delta H is positive. So you might have a delta H of positive 75 kilojoules per mole. Okay, in the lab you're going to try and find out the enthalpy change of reaction, so that's the heat energy transferred when copper sulfate reacts with zinc to make zinc sulfate and copper, and you probably recognise that as a displacement reaction. Displacement reaction. The apparatus you're going to use is a coffee cup calorimeter, which consists of a polystyrene coffee cup sitting in a 250 milliliter beaker, and inside the coffee cup you're going to put copper sulfate solution and zinc powder, and then you're going to stir it with a thermometer and measure the temperature rise. So let's imagine that in our experiment you reacted 25 centimeters cubed of copper sulfate solution, and that's 1 cubed, and you react it with excess zinc. So, in other words, all of the copper sulfate that you put in will react. Later on, you'll need to know exactly how many moles of copper sulfate have reacted. So let's just quickly calculate how much copper sulfate we've used. It's 25 centimetre cubed of copper sulfate and it's 1 mole per litre. So hopefully you remember the equation. Amount in moles equals concentration times volume. So the concentration is 1 mole per litre, and the volume is 25 divided by 1,000 decimeters cubed. So remember to divide by 1,000 to convert centimeters cubed into decimeters cubed, and that gives us 0.025. Sorry, not D, but 0.025 moles. Okay, so we put 25 centimeters cubed of copper sulfate in and react it completely until the temperature doesn't go up anymore. And let's say, for the sake of argument, that the temperature rise, delta T, is 30 degrees centigrade. That's 30 Kelvin. So a lot of the time now we're going to be using the Kelvin scale for temperature. So in order to understand that, you need to understand that 1 degree centigrade is the same as 1 Kelvin. Right, now for the calculation. So let's just recap. We reacted 25 centimeters cubed of copper sulfate solution with excess zinc powder. So all of the copper sulfate reacted. That was 0.025 moles of copper sulfate. And the temperature rise that we measured was 30 degrees centigrade. So here's how you carry out the calculation. First of all, you need to use this important equation. Energy transferred equals mass of water times specific heat capacity of water times the temperature rise. You should be familiar with this from GCSE. You may have seen it in the form energy equals M times C times delta T, mass of water times the specific heat capacity times the change in temperature. So let's put in our numbers. First of all, the mass of water. Well, we're going to make some assumptions here. The first assumption is that we used 25 grams of water because we used 25 centimeters cubed of copper sulfate. So we've assumed that 25 centimeters cubed of copper sulfate solution contains 25 grams of water. It's an approximation. The specific heat capacity of water you'll need to be given, so that's 4.18 joules per gram per Kelvin, and then temperature rise, we measured that as being 30 degrees centigrade. Now the next step is to calculate the enthalpy change per mole of copper sulfate that reacted. So the equation we're going to use to do that is that delta H reaction, the enthalpy change of reaction, equals the energy transferred divided by the number of moles that reacted. So the energy transferred was 3135 joules. We're going to divide that by the number of moles, which was 0.025 moles. So put that into the calculator and we get 125,400 joules. First step, convert it to kilojoules, so that's 125.4 kilojoules. Give it a minus sign, because if you remember from the first slide that exothermic reactions have negative signs, and that's the value for delta H reaction. So we made a couple of assumptions in this calculation. The first assumption we've already mentioned. We assumed that 25 centimeters cubed of copper sulfate contained 25 grams of water. So in other words, we assumed that the density of our solution was 1 gram per centimeter cubed. The second assumption that we've made is that the specific heat capacity, 4.18 joules per gram per Kelvin, is the same for our water as it is for our copper sulfate solution. Again, it's another approximation. Okay, here's a challenge calculation for you to see if you've understood what we've been doing. So 100 centimeters cubed of copper sulfate, which is 0.5 moles per litre, reacts with zinc in a coffee cup calorimeter, and this time it gives a temperature rise of 18 degrees centigrade. See if you can calculate the enthalpy change of reaction, again assuming that the specific heat capacity of